Good morning, all. So we will proceed with the next supervised learning approach. So in the previous lecture, I have discussed about decision tree and its attribute selection features. Now in this lecture, we will learn about naive-Bayes classifier. So naive-Bayes classifier, as the word itself says, naive. So it is a very basic or fundamental classifier. It's very primitive in nature and it mainly works based on the probability matrix. So Bayesian classification primarily looks at the probability of occurrence of a particular um class or label. So what is the probability that the person plans to buy this laptop? Yes, okay, or no. So it primarily calculates the explicit probabilities for hypothesis among the most practical approaches to certain types of learning problems. So incremental, each training example can incrementally increase or decrease the probability that a hypothesis is correct. One of the major drawbacks with naive-Bayes classifier is that it considers every attribute or every class or feature to be independent of each other, which is not really true, because if you look at the person who buys a computer, it cannot be determined by just age or credit rating or whether the person is a student or not. We rather have to consider multiple such independent features or independent factors in order to arrive at a decision that, considering if the person is a student and is a middle age and his credit rating is excellent, then we consider then the decision can most likely be made that he buys a computer. So this is one of the inherent drawback of naive-Bayes classifier, because it considers every attribute or every class, every attribute of the data set is considered to be independent of each other. So all these probabilities can be estimated from the training set, possibly using smoothing. So for new records to be classified, we know whether each of the events have occurred or not. So we want to find out whether event P is true. So all of us are familiar with Bayes theorem. So the probability of occurrence of A given B can be given in this manner. So probability of A to probability of B, dot product of probability of B given A. Okay. So what we are actually looking at here is the prior probability to post probability. A priori probability before to the probability after. So what is the probability of occurrence? So test set can be classified, which represents a young student with fair credit rating. So statistical independence is what is been assumed. That is actually a drawback with the naive Bayesian classification. So how do we classify a new record considering the estimation of occurrence of class C given D? So assign D to the class having the highest probability. Now if we take the same example that we have used for the decision tree, where we are trying to understand who buys the computer. Okay. So we again take the count of number of yeses to no's, so which we have already found that we have 9 yeses with 5 no's. And then here in this case, instead of calculating information gain, entropy, or Gini index, we calculate the probabilities of each attribute, because this is a probability driven classifier. So the probability of youth to yeses, probability of middle to yes, probability of senior to yes. So how many youth have said yes, how many middle have said yes, how many seniors have said yes. So we take the count and then we divide it by the total number of counts. So that gives us a probability value. Similar case with no's also. Then we continue with other attributes, namely the income attribute and student attribute, and similarly the credit attribute. So in the income attribute, again we do the same procedure, find out the probability of low income to yeses, low income to nos. So once we have calculated the probability values for each of these attributes, namely age, income, student, and credit rating, then we apply the Bayes theorem to yeses to nos, right? So we classify an unseen set. So for example, if x is less than age, youth is x is less than age, that is youth, and income is low, and the student is yes, credit is fair. So compare the probability of these to x and probability of no's to x. So we combine youth, low, yes, and fair, considering age, income, student, and credit. Okay, so overall we are getting 0.0211. Similarly, for no's also we calculate the probability, we are getting 0.0034. Since the probability of yeses multiplied by the probability of actual probability of Bayes computer is greater than the probability of no's multiplied by the probability of no's, so x can be classified as Bayes computer. Okay, so we can conclude saying that the if the counts, if the probability of occurrence of yeses is more or higher than the probability of occurrence of no's, then we can conclude that whatever the test case data that is been given here, so this is your test case data. So the test case data says that x to be considered as age is youth and income is low and student is yes and credit is fair. So if you given this test case, what is the outcome of the Bayes computer? So from this, once we calculate the probability of occurrence of yeses to nos based on the data that we have for age attribute, income attribute, student attribute, credit attribute, so we find that the probability of yeses is 0.0211, so which is higher than compared to 0.0034. Hence, we conclude that for the given test case, it is likely that the person will buy the computer. Okay. So this is naive-Bayes classifier. So it is robust to isolate noise points. It can very well handle missing values by ignoring the instance during probability estimate calculations. It is also robust to irrelevant attributes because this classifier doesn't really bother about noise and missing values and entities, because the entire classifier revolves around probabilistic approach. So it mainly looks at by what count a particular category exists in the data set, right? So this is a very primitive, and hence it is called as a naive-Bayes classifier. One of the drawback with this one is independent assumption may not hold for some attributes. So it assumes that every attribute is independent of the other, which is not really true, because if you consider the salary of an employee, it could rather depend on the age and his education qualifications and the number of years of experience, which all could contribute to a salary of the employee. So not just one single attribute. Okay, then let's proceed with the so with this the naive-Bayes classifier is completed. Now we are proceeding towards the k nearest neighbor classifier. This is another very interesting classifier in the supervised learning approach. So this classifier mainly is based on the distance metric. There are two types of, although there are several other distance measures that can be taken into account, but very popular distance metrics that are usually considered for k nearest neighbor classifier is either Euclidean distance or Manhattan distance. In addition to this, you also have Bhattacharya's distance and Mahalanobis distance. Several other distance metrics are also considered. So depending on the problem and the data set that you are handling, if it is astronomical data, then probably you will look at Bhattacharya or Mahalanobis distance. For non-astronomical data or geo-coordinate projection data, where your data is normally in a non-geo-coordinate data or astronomical data, then we could usually apply Euclidean or Manhattan distance. So what is this k nearest neighbor? What does the k actually stand for? K actually means how many number of neighbors that you are actually going to consider for your classification problem. So trying an example in Euclidean space. So if you consider X belongs to a rational set of data, and that is belonging to a Euclidean space. Now in this case, the idea is the value of the target function for a new query is estimated from the known values of the nearest training examples. So you will be identifying the value of a target function by estimating the known values of the nearest training examples. So distance is typically defined by using the Euclidean distance measure, that is the mod of xa minus mod of minus xb. So that is root summation of xj of a minus xj of b whole square, right? So the algorithm for the implementing the k nearest neighbor is there are two-step process. The first step is you will find the examples that are closest to the proximity of a selected data point. So x and t from the stored training set closest to the test instance x, closest to the test instance x. So x star is arg min of distance. So we are trying to identify the minimal distance. So there are test points which are at a very closest to the target point that we are looking at. So we always look for arg min, not arg max, because arg min, the minimum is the distance, so that we can include and consider the data point as the nearest neighbor. So and then we output that as y. So the nearest neighbor algorithm does not explicitly compute decision boundaries, but these can be inferred by showing the but these can be inferred based on the distance, how close in by how close proximity or the target data points to the the data points in the data set to the target data point. So we could represent this with the help of Voronoi diagrams through Voronoi diagram visualization, so which shows how input space is divided into classes. So if you visualize your entire Euclidean space data points in this manner, then all these data points are segregated. So if we are looking for a target data point, what are the closest data points which are in proximity to this target data point? So each line segment is equidistant between two points of opposite classes. So we have black dots with red dots. So all these gray colored zone or area that you are seeing is all belonging to one particular class, and the white area with black dots is all belonging to another class, because all these are at equidistant to each other. So similarly, if you represent this in two-dimensional decision boundary considering width and height, then all these data points are all at close proximity, and all the blue triangles are all at the close proximity. So basically the idea of nearest neighbor is how close can you identify your neighbors based on the closest proximity. So decision boundaries of the neighbors in the close proximity are considered for classifying the data. So in the three-dimensional space also, if you look at the gray space versus the red space with black dots and red dots. So this is how it depicts for the k nearest neighbor. Approach can work with multimodal data. So one of the benefits with k nearest neighbor as compared to decision tree or naive based classifier is that this classifier works with multimodal data. If the data is organized in different forms, where you don't really have to draw or separate the data space into by using one diagonal line as such. So separating them into two separate classes. So even if your data is spread all over and it's in multi-model fashion like this, the k nearest neighbor will still be able to give, will be able to perform the classification and give better results. So as we can see here, the blue dots are all been segregated as one colony of neighbors, and all the red dots are all plotted in the in the form of a sigmoid shape, S shape, and they all form together as one colony of neighbors. So k nearest neighbor works very well for multimodal data, which is not possible for the earlier with the earlier classifiers that we have discussed. So nearest neighbors, one of the you can say the disadvantage here is it's sensitive to mislabeled data or class noise, because if your data has noisy samples, and since this works with multimodal data, every example in the blue shaded area will be misclassified as blue class because it is in the close proximity, because it's only relying on the distance metric. So smooth. So one way to control this noisy behavior in the data set is by smoothing the k nearest neighbor distance metric. So if you try to analyze the data points which are in close proximity, okay, and then revalidate the classifier to see if they actually belong to this class or not. So find k examples closest to the test instance. Classification output is majority class. So here we consider the argmax. So here we not just considered one single data point and considering this point to identify the proximity of the data points. Rather, we collect the proximity information from the closest data points to the target data point that we are trying to combine and consider as a nearest neighbor. So if you are voting majority of the data points which are in proximity to the target point, also confirm that this data point or the target point is in close proximity to them as well as the target data point, then we can consider. So majority of the proximity values have to be taken into consideration before you actually decide this data point to be a neighbor of the target class. So how do we choose k here? So larger the k may lead to better performance, no doubt about it, because you are going to combine several neighbors. So as a result, your class can be high. But at the same time, when you increase the k value, you are also likely to overfit the model because the noise might also join as a neighbor. So if we set k too large, we may end up looking at samples that are not neighbors, but they pretend to be neighbors because we are simply looking at the proximity of distance, right? So one way to control this is if you apply cross validation to find k, to see how many to what extent are these neighbors can actually qualify as neighbors. So one rule of thumb, very precisely specified out of worked out examples, is if k value should ideally be less than the square root of n. If there are total number of data points, let's say if there are 625 data points, so square root of 625, ideally your k should not be beyond 25. So the maximum number of neighbors that you could expect is 25. It should be way below that, right? So number is the number of training examples that you are looking at. So k should be less than the square root of n. So for some attributes, the coordinates of x have larger ranges, so they can be treated as more important. So one way to handle that is you can normalize the scale, because larger scale, the range of each features can be in the range between 0 and 1. So linear scale, the dimensions can have 0 mean and variance 1. So mean and variances for an attribute can be used to scale the data points. Uh, the other aspect is some of these attributes may be irrelevant and they are highly correlated also. So which if their correlation between the data points is high, they actually add noise to distance measures. So we have to eliminate such attributes, and these attributes can also vary or possibly adapt weight of attributes. So in addition to this, we will also have another issue to look at, that is non-metric attributes or symbols. So for example, if you are considering non-distance metric mechanisms like Hamming distance, so which might be completely different as compared to Euclidean and Manhattan distance metric. So in Hamming distance, you consider based on the symbols. So for those kind of data where you are considering non-metric attributes, k-nearest neighbor classifier is not at all suitable. So you will have to look for a different classification approach rather than k-nearest neighbor classifier. Now, in terms of complexity, it is expensive at test time because as the number of samples increase, one largest near neighbor must compute the distance of all n training examples. So big O of k times dn. So use subset of dimensions, pre-sort training examples into fast data structures. So there is another very popular data structure which which can be applied to improve the complexity, to reduce the complexity of the k-nearest classifier. So they are called as KD trees. So we compute only an approximate distance. So again, the approximate distance can be looked at as what kind of distance metric you are applying, and also remove redundant data. So condensing of samples is also another technique where you reduce the Euclidean landscape to be extended to far higher data points, and then you combine them into condense them to reduce the data size. Storage requirements must store all training data, so remove redundant data. Pre-sorting often increases the storage requirements. High dimensional data, mainly the curse of dimensionality. So computational costs also increase. Now let's look at a sample problem using the k-nearest neighbor. So let's say we have a about company which is actually into baby products. So they have identified two factors. So first factor is the growth of the baby and then the intelligence. And based on these two factors, we want to classify whether these two should be considered, what factors, by what proportion these two factors have to be considered for the new product that they are planning to launch. So let's say the new product that they are planning to launch has a growth factor of 3 and intelligence of 7. So will the classification stand out to be good or bad, right? So we compute for test case x1 equal to 3 and x2 for 7, considering that 3 nearest neighbors are considered. Compute the distance among the training samples. So the data is having 4 data points pertaining to growth and intelligence, and if growth and intelligence happen to be 7, the classification is saying that it is bad for the growth of the child, growth of the baby. And if the growth is 3 and intelligence is 4, and it's considered as good, as a good product for baby. So we have to see what this classifier does when we consider growth to be 3 and intelligence to be 7, considering the 3 nearest neighbors are considered at the time. So the computation goes like this. So we compute the distance among the training examples. So we first identify, apply the Euclidean distance metric here. So when we apply, the first row happens to be 4, and second happens to be 5, and third happens to be 3, and fourth one happens to be 3.13. Now, if we rank all these data points, then it turns out to be that the third row gets the first rank, then followed by the fourth one, then followed by first, then followed by the second. So, considering simple majority of the training sample, which tells us whether the new launch product is good or bad. So from obtained distance, it can be classified to three nearest neighbors. If yes, then it is good, else it is bad. So if you look at the parameters that qualify for 3, closest to 3, so 3.3 is exactly the 3. So 3 happens to be 3, so that is the first one. Then the next available proximity is 3.13, then after that 4, and then 5. So um, so as a conclusion, so if the test data, as per the test data, it says that x is 3 and x2 is 7. Okay, x. So as more good class exists, okay. So as more once we put all this data into application, so considering 3 and 7, so 7 minus 3 plus 7 minus 7, because our test case provided is 3 and 7. So once we apply the Euclidean distance metric, then we rank it, and then based on that we identify the classes generated. So the first one is good, second one is good, 1 and 2. So it should be way below the three nearest neighbors. So we cannot go beyond that. So 1 and 2 is okay. 3 is bad because exactly on 3 it's not possible. 4 is also out of proximity. So as we can see that majority of them are saying good. So it turns out to be that the product is good for the child growth and intelligence. Okay. So with this I conclude this um, presentation on the k nearest neighbor classifier. So let's after this we will discuss on another classifier um, approach, classifier model for supervised learning.